Great. Okay. Well, thanks everyone for coming along today for the first seminar of this year in the AFMS series. So it's my pleasure to introduce our first speaker, Dr. Milad Samie, who is an adjunct professor and a postdoc research fellow at Queen's University. Milad received his PhD from the University of Melbourne back in 2018 under the supervision of Professor Ivan Maruzic and Prof. Nicholas Hutchins. So Milad likes to use experimental and theoretical methods to study various fundamental flow physics. All right, take it away, Milad.
Thanks, Kath, for the introduction. So today I'm going to talk about eddy structures and very large-scale motions in turbulent round jets. I just wanted to ask the audience if you have any questions during my talk. We can speak up. It can be an interactive talk. Okay, so here is a brief outline of my talk. I'll start with an introduction on the eddy structures and very large-scale motions in turbulent flows. Then I'll introduce the linear currency spectrum, which is an analysis tool that I'm going to use for this study. I believe that Dr. Wotan Bars has already talked about linear currency spectrum in one of the previous talks in the same seminar series. He used the linear currency spectrum in the context of wall-bonded turbulent flows. I'll use it for the jet flows. And after that, I'll present some results regarding current structures in the turbulent round jets, and I'll present my concluding remarks and future work. So current structures are important phenomena in mixing, drag, noise generation, heat transfer, and many other different phenomena in fluid flows. So understanding them helps us better control the flows. We can improve noise reduction, improve heat transfer, mixing, etc. And they exist in a variety of length scales in turbulent flows. So here you see an image that shows the concentration field in turbulent jets. We can see there are very different scales of eddies. The largest ones are of the order of the boundary layer thickness, and there are medium-sized eddies and very, very smaller eddies that are the size as the Kolmogorov length scale. So these are eddy structures, but on the other hand, we have the very large-scale motions that are believed to form by concatenation of the eddy structures and form very long structures. So in the middle, the figure shows the streamwise velocity fluctuations in a wall-bonded turbulent flow on a streamwise, spanwise plane. This is a figure from Hutchins and Maruzic. The dark regions show the low speed regions in the flow. You can see the length of these structures can be as high as 20 times boundary layer thickness. So they are very long. Also, these very large scale motions have been reported in jet flows, for example. Here we're seeing a helical structure in jet flows reported by Milad Samie et al. In 2018. So the main difference between the very large scale structures and eddy structures is their length. The very large scale motions can length is of the order of 10 times delta, 10 times the boundary layer thickness, and for the eddy structures, their length scale is usually of the order of the boundary layer thickness or smaller. So we are in this talk, we're interested in the very large scale motions and eddy structures in the jets. So for the very large scale motions, they have been categorized in the literature as the rings, helices, and double helices. This is a cartoon from Fisu and Hussein, and also in more recent studies like this one, they have been reported in turbulent jets. But on the other hand, we have the eddy structures, which, as I explained in the previous slide, are smaller scale structures. So eddy structures in the jets have not been studied as much as they have been studied in boundary layers. This is one of the few studies by Matsuda et al., where we can see these C-shaped eddy structures in the flow. So I'll start with the eddy structures in a wall-bounded flow. So here we see a flow field from a tomographic PIV from the study of Elsinga et al. And here is an instantaneous flow field where the eddy structures are shown by the green isosurfaces. Here, Q criterion has been used to visualize the eddy structures, and the blue surfaces show the lowest speed region. The lowest speed region is where the velocity fluctuation is negative. Basically, the speed in the flow is lower than the mean velocity in the flow. Now, if we look at this small box here and zoom in, this is what we see. So we can see that these eddy structures, the green tube-shaped structures, kind of hug the low speed region. And we can look at, if we look at the cross sections, so for example, this wall normal streamwise cross section of this flow field, and look at the velocity vectors, you can see where we cut through the eddy structures. We have these swirling regions, swirling flow regions around the eddy structures. Also, on a span-wise, stream-wise cross stream, again we see these rotational flow fields when we cut through the eddy structures. But we can also conditionally average the eddy structure. So Elsinga et al. Used the linear stochastic estimation to conditionally average the eddy structures. So now this figures show these conditionally averaged structures. First of all, you can see that an eddy structure is at an angle with the streamwise axis, and the leg. So these are the legs of the eddy structure, and this is the head of the eddy. The legs are located upstream of the eddy. So this and we say that the eddy is backwards facing. Now we can again look at the cross surfaces. This is a wall normal streamwise cross surface, and we can see that where we cross through the head of the eddy, we have this swirling region or the swirling flow caused by the head of the eddy, and these two swirling regions caused by the legs of the eddy when we look at the span-wise, streamwise plane. So these rotational regions are called the eddy signature. The other thing about the eddy structures or hairpin vortices in wall-bounded flows is that they are it's known that they are hierarchical and self-similar. So here on the left, I'm showing a cartoon from Bars et al., where 4 hierarchy or 4 eddy sizes are shown. So the largest rectangle represents the largest eddy structures, and the smaller ones represent the smaller eddy structures. So it's known that the eddy structures in wall-bounded flows are hierarchical and also self-similar. But now we can take a look at the literature, what has been presented or reported in terms of the eddy structures in the jet flows. So here in the study of Matsuda et al., which is one of the few papers on the eddy structures in the jets, they used time-resolved stereo PIV to capture the velocity components, and use swirling strength to visualize the hairpin vortices or eddy structures. We can so here we're looking at two Reynolds numbers. These are instantaneous flow fields. One is Reynolds number at 1500, the other one 5000. And in both of them, we can clearly see these C-shaped eddy structures. And by the way, the flow direction is shown by the arrow. And here on the left, we are looking at a cross-flow plane, where so the center line of the jet is located here, and we can see that the C-shaped eddy structures are positioned around the rim of the jet. So the legs are closer to the center line, and the heads of these eddies are facing away from the center line. And Matsuda et al. Also computed the conditionally averaged eddy structures, and this is what they obtained. So here we're looking at the conditionally averaged eddy structure from three views. This is a side view, so we can see that similar to wall-bonded flows, it appears that the eddy structures in jet flows also are located at an angle with respect to the streamwise direction. But the difference here is that the leg of the eddy is located downstream of the head of the eddy, and the other difference is that the flow field inside the legs or between the legs of the eddy is positive. So we have a high speed region between the legs of the eddies and two low speed regions outside, which is opposite to the eddy structures in wall-bonded flows, where we had a low speed region between the legs of the eddy. Now, with this introduction, we pose some questions that we try to address in this talk about the coordinate structures in turbulent round jets. So the questions are if the eddies in the jets are hierarchical or self-similar. The other question is if the eddies and how the eddies and very large scale motions in the jets are linked. And finally, what do the very large scale motions look like? To answer these questions, we conducted a series of measurements in a jet facility located at Queen's University. The jet velocity profile is top hat, so the velocity, the jet is laminar, leaving the jet nozzle, and because of the Kelvin-Helmholtz instabilities, it transitions to turbulent, and where we conduct the measurements, which is 15 times diameter of the jet nozzle, downstream of the nozzle, the flow is fully turbulent, and the Reynolds number for these measurements is 50,000 in terms of the jet diameter and the jet velocity. For the measurements, we used two hot wires, so we acquired the velocity fluctuations simultaneously using these two hot wires, and we used two arrangements for the hot wires. In the first one, which is a radial arrangement, we've located a reference hot wire, which was fixed at a location that is YRF. Its distance from the center line is shown by YRF. And the second hot wire, which was traversed in the radial direction incrementally, from very far away from the first hot wire towards the fixed hot wire. So in the first arrangement, the separation between the fixed hot wire and the traversing hot wire is in the radial direction. But in the second one, which is an azimuthal arrangement, so if we look at the cross section of the jet, we can see something like this. So first hot wire is fixed, and a second hot wire, which is traversed on the perimeter of a circle at various locations. So the distance between these two hot wires in this arrangement is shown by delta S, and we are looking at the azimuthal distance between the hot wires. And also the radial distance of the hot wires in this arrangement is the same. So when we acquire the velocity signal simultaneously with these two hot wires, we calculate the linear coherence spectrum, which is basically a scale-dependent correlation between two signals. So what linear coherence spectrum gives us is, in fact, the coherence magnitude between two signals at various frequencies or wavelengths. And the way we calculate it, we take Fourier transform of two velocity signals from hot wire 1 and hot wire 2, multiply one of them by the complex conjugate of the other one, and do this for many realizations, take the ensemble average of them and calculate the modulus, and finally normalize it. So as you can see, coherence is a function of delta y, the distance between the hot wires here, and the wavelength, and it's always between 0 and 1. 1 is when we have two identical signals, and when the signals have no coherence whatsoever, then gamma squared is 0. And also because we use hot wire signals, signals are in terms of time. So when we calculate the Fourier transform, we have this coherence in terms of frequency. So we use Taylor's turbulence hypothesis to convert the frequency to wavelength. Now, I want to show what a typical LCS linear coherence spectrum looks like. So suppose we have these two hot wires, or these two velocity time series from these two hot wires. Because they are located at a finite distance from each other, the signals are not identical. So when we look at the coherence for relatively small wavelengths, the coherence is 0. And when we move to larger wavelengths, at some point the coherence picks up and increases until it reaches a wavelength where it flattens out. So this is a typical LCS in a turbulent flow. Now, in this slide and the next few slides, I'm going to conceptually construct the linear coherence spectrum for a jet flow, with the assumption that the flow is populated with hierarchical eddy structures. So for this illustration, I use 4 eddy sizes. So these rectangles represent eddy sizes, eddies of different sizes. So each of these rectangles represent an eddy hierarchy in the jet flow. And for the illustration only, we use 4 eddy sizes. Suppose we have a hot wire, which is the reference hot wire and located at y = 0. And we have another hot wire that is within the flow field of the largest eddy. So now at this position, both the hot wires, the fixed hot wire and the traversing hot wire, so we're going to traverse this one closer later on. Both of these hot wires are measuring the flow field created by the largest eddy, and the length of this eddy is L1. Now, proportional to this length, L1, is a wavelength, lambda 1. And for wavelengths smaller than lambda 1, because eddy doesn't have any, the largest eddy doesn't have any energy, then coherence is 0. And for wavelengths greater than lambda 1, we have some finite coherence. Now this coherence can be have a finite value for up to very large wavelengths, and that's because of the repetition of these eddies in the streamwise direction. So what happens is effectively a very long structure is made by repetition of these eddy structures in the streamwise direction, and as a result, we have non-zero coherence up to very large wavelengths. Now, if we move the hot wire or the traversing sensor closer to the reference sensor, so that now both sensors measure the velocity flow field created by the first and second eddy hierarchies. Now, because the second eddy has a length of L2, which is smaller than L1, there is associated with that a wavelength lambda 2. So lambda 2 is smaller than lambda 1. Therefore, we will get a finite value of coherence here. And for wavelengths greater than lambda 1, the effect of these two eddy structures is effectively superimposed. So what we get is that coherence from the second eddy is added to coherence from the first eddy. Therefore, the magnitude of coherence increases in this region for wavelengths larger than lambda 1. Now we can continue this process closer and closer, and we get these staircase-like coherence plots. What is important here is by decreasing delta y, the magnitude of the coherence increases, and at the same time, because the eddies effectively measure the flow field by smaller and smaller eddies, the coherence encompasses smaller and smaller wavelengths. Now, because lambda L is a function of delta y and a wavelength, we can create coherence spectrograms where we plot coherence, gamma L, as a function of delta y and wavelength. So here we're showing the isocontours of coherence, and lighter colors show lower coherence values, and darker colors show higher coherence values. You can see that by increasing wavelength and decreasing delta y, we get higher coherence values. Now, this coherence spectrogram is constructed for 4 eddy sizes. Now, if we had a more realistic type of flow, where we had a continuous spectrum of eddy sizes, it's not difficult to show that these staircase isocontours converge to these smooth isocontours. And another important point here is that in this staircase type of isocontours, we could see lambda 1, lambda 2, and lambda 3, and lambda 4, which are associated with these 4 hierarchy of eddies. However, when we have a continuous spectrum of eddy sizes, the only wavelength that is visually distinguishable is lambda 1, which is associated with the largest eddy size. So effectively, just by looking at the coherence spectrogram, we can say that this region is associated with the eddy structures, and this region where the isocontours become independent of wavelength, they are associated with the very large scale motions, which are formed by the repetition of eddy structures in the streamwise direction. Now, we can compare this conceptual construction of the coherence spectrogram with some spectrogram from the experiment, and we can see that the experimental spectrogram resembles to the conceptual spectrogram. We have this eddy structure spectral domain and this VLSM spectral domain. So another piece of information that we can derive from the linear coherence spectrogram is the self-similarity of eddy structures. So we can see that the aspect ratio of the eddies, which is given by the ratio of the length of the eddy to the height of the eddy. So if all the eddies are geometrically self-similar, meaning that L1 to delta Y1 is equal to L1 to delta Y2, etc., is a constant, we can show that the isocontours on the linear coherence spectrogram are parallel to the lines that show proportionality between delta Y and wavelength, the height of the eddies to the wavelength of the eddies. In that case, we can fit a curve fit like this to the isocontours, or the coherence surfaces, and by equating the linear coherence spectrogram to 0, we can define the aspect ratio. So aspect ratio, as was defined first time, I guess, by Bars et al., is defined or obtained when we equate this equation to 0 and find lambda x by delta y at this value. So this aspect ratio is a spectral aspect ratio because we have a wavelength here. So this is different from the physical aspect ratio of the eddies, but is proportional, in fact, to the physical aspect ratio of the eddies, because lambda x, the wavelength associated to each eddy, is proportional to the streamwise length of that eddy. So I just want to summarize all the information that we can extract from a linear coherence spectrogram. We can estimate the aspect ratio of the eddies. We can estimate the spectral boundary, which is this one, between the eddy structures and very large scale motions. And these arguments that I presented so far were proposed for the radial distance between the sensors, but they apply to azimuthal separations between the sensors too. So with that, I can present some experimental results. So here I'm showing two experimental linear coherence spectrograms. One is for the radial measurement, and the other is for the azimuthal measurement, as you can see in these cartoons below. So in both of them, you can see that we have these eddy structures where, or the signature of the eddy structures where the isocontours are parallel to this line, which is lambda x equals 4.7 times delta y, which shows proportionality between the wavelength and the distance between the sensors. And this constant 4.7 is in fact the aspect ratio, the spectral aspect ratio of the eddy structures. We also can see that the boundary between the eddy structures and VLSMs is lambda x equals 4 times the jet half width. And these pieces of information are true for both azimuthal arrangement and the radial arrangement. So we can gain a three-dimensional view of the eddy structures in the jet flow. So based on these results, we can see that the eddy structures, first of all, are hierarchical and self-similar in the jet. And also, we found a spectral aspect ratio in the streamwise radial direction and also streamwise azimuthal direction, which is equal to 4.7. We also found a spectral boundary between the eddy structures and VLSMs that is represented by this equation. Wavelength lambda x is equal to 4 times the jet half width. Now, a couple of notes on these conclusions. First of all, if we compare these this aspect ratio for the jet with the aspect ratio found for wall-bonded turbulent flows, we can see that so the aspect ratio for wall-bonded flows is 28. This was reported by Baidia et al. In 2019 for pipe flows. You can see that the eddy structures are much longer in wall-bonded flows compared to jet flows. So this long eddy structures, in fact, are in accordance with the notion of packets of eddies, where a large number of eddy structures are form a packet of eddy in the streamwise direction. While this small aspect ratio, relatively small aspect ratio in the jet flows suggests that probably eddy packets do not exist in the jets. And also, with this spectral boundary between the eddy structures and VLSMs, we can form a filter where this wavelength can be used as the filter corner frequency or filter corner wavelength to separate the VLSMs from the rest of the flow. And so we're going to use this filter. And this plot shows a sample velocity signal and the filter used to separate the very large scale motion. So you can see that the gray line shows the raw signal, and the thick black line shows the filtered signal that we have. In this filter, we have used this wavelength as a corner frequency and use it on the time series. So we're going to use these filtered velocity signals to look at the configuration of the VLSMs in the jet flows. And to do that, we use a correlation. So first of all, before jumping into the filtered correlation, I look at the correlation from the raw signals. So here I'm showing two correlation maps. First one for the radial arrangement of the hot wires, and the second one on the right is for the azimuthal arrangement of the hot wires. In the radial arrangement, first of all, we can see that the correlation map shows a structure that is that forms an angle with respect to the streamwise axis. And this kind of suggests that the structures in the radial direction form an angle with respect to the x-axis. But in the azimuthal arrangement, so this is delta S, the azimuthal distance between the hot wires, we can see that we have a positive correlation region, and alongside of that, we have a negative correlation region, which shows that we have in a statistical sense, we have a high speed region, and alongside of it, in the azimuthal direction, we have a low speed region. Now, if we filter out the eddy structures and just retain, just keep the very large scale motions in the velocity signal and calculate the correlation from these very large scale component of the velocities, this is what we get. So interestingly, we get two, in both of the radial arrangement and azimuthal arrangement, we get these negative correlation regions alongside the main positive correlation region in the streamwise direction for both the azimuthal and radial arrangement. So now if I just focus on the azimuthal measurements and the VLSM correlation. Based on this observation, we hypothesized that the VLSMs have to be at an oblique angle with the jet axis to be able to create these negative correlation lobes alongside the streamwise direction. So to test this hypothesis, we created two synthetic flow fields. These synthetic flow fields are created in the streamwise spanwise planes, and these structures are meant to simulate the VLSMs in the jet, the very large scale motions in the jets, and contain a high speed region flanked by these two low speed regions. So in the first synthetic flow field, we use axially aligned structures, as you can see here. So this is just one structure. We used several hundreds of these structures and randomly distributed them to create a flow field. And the second synthetic flow field, we used oblique structures. So then we calculated the correlation maps for the flow fields associated with these structures, these two structures. And this is what we get. Now, if we compare these correlation maps with the experimental correlation map from the VLSM, in fact, the VLSM component of the correlation map, we see that this one, which is associated with the oblique structures, resembles the, qualitatively at least, resembles the experimental correlation map. Particularly, we see these negative correlation lobes in the streamwise direction in the experiment and in the synthetic flow field. So these results support our hypothesis that VLSMs in turbulent jets are oblique structures in the two-dimensional streamwise, spanwise planes. We also looked at some instantaneous streamwise flow fields from some DNS data from Shin et al. 2017. So here, this flow field shows this streamwise velocity fluctuations on an unwrapped cone. Red color shows positive velocity fluctuations, and blue color shows negative velocity fluctuations. And the reason why we have an unwrapped cone, so this is a streamwise direction and this is azimuthal direction. And the reason why we have an unwrapped cone rather than an unwrapped cylinder, for example, if we were looking at the flow in a pipe, we would normally have an unwrapped cylinder because the radius of the pipe is a constant. But in a jet flow, because the jet hop width grows with x, and we want to be able to follow the structures that grow with the jet, we look at a cone and unwrap it, so the result looks like a triangle. So I just wanted to explain to make sure that everyone understands this flow field. So if we look at the structures in this flow field, you can see that for streamwise locations larger than 15, the eddy structures seem to be angled with respect to the x-axis. So we have both positive angles and negative angled structures, which kind of, in the instantaneous sense, support our observation from the correlation maps as well. So these show that the eddy structure, the very large scale motions make an oblique angle with the streamwise axis too. Now, if I look at a smaller box in this flow field and zoom in, So this is a zoom in view of that box, and overlay the velocity vectors on the streamwise velocity fluctuations. We can see that there are several swirling regions. As you can see, they are demarcated by these circles. You can see these circular regions in the flow field that are mainly located on the borders of the high speed region, the red regions and the blue regions. So these rotational flow regions are reminiscent of these the signatures of the eddy structures from the conditionally averaged flows. So, for example, we saw that in wall-bounded flows, when we cut through an eddy structure, the effect or the flow around the legs of the eddies form these circular motions. So this plot suggests that these circular regions are in fact signatures of the eddy structures, and these eddy structures concatenate and form these very large scale motions in the jet. So based on all these observations, we propose a simple conceptual model for the eddy structures and VLSMs in turbulent jets. So this is our model for the eddy structure. The green tube shows the eddy, and we have a high speed region between the legs of the eddy and two low speed regions outside the legs. So this is an isometric view, and this is a top view of the eddy. And it seems that the eddy structures prefer to form a VLSM that makes an oblique angle with the streamwise direction rather than an axial aligned structure. So this is a two-dimensional view of the VLSM on the streamwise azimuthal plane, and a three-dimensional view of this VLSM becomes this helical structure, which is comprised of a high speed region flanked by two long low speed regions. So this brings me to the concluding remarks. We showed that using the linear coherence spectrum, we showed that eddy structures are hierarchical and self-similar in turbulent jets, very much similar to wall-bounded flows. But the eddy structures in the jets are noticeably shorter compared to the eddy structures in wall-bounded flows. We can use the linear coherence spectrogram to separate the eddy structures and VLSMs in any turbulent shear flows. And using this method, we showed that the helical structures are the dominant VLSMs in turbulent round jets. And the way it works is apparently that eddy structures concatenate and form these long helical VLSMs. So in the future, this is in fact what we are currently looking at. We are trying to visualize the eddy structures and VLSMs in three-dimensional data set. So here you can see a preliminary result that we have conditionally averaged these very large scale helical structures, and it seems that in fact the eddy structures are embedded in these three-dimensional helical structures. And with that, I conclude my talk. And at this stage, first I want to thank you for listening to my talk. And I also want to acknowledge my co-authors, Dr. Pollard and Philippe Lavoie, who I've been working with during my postdoc at Queen's University, and also Dong Hyuk Shin and Vlad from Korea Advanced Institute of Science and Technology for providing their DNS data, and finally the organizing committee for organizing these seminar series. Thank you.
Great. Well, thank you so much for the talk. I always love hearing about these very large scale motions and eddy structures. So it was really cool to be able to see that in terms of the jet as well as the wall-bounded flow. We do have some time for questions. If you're in the audience, feel free to jump in, or you can raise your hand and I can call on you. Or you can also write in the chat and I can read out as well. Cool. Maybe just to get things started while people are thinking of their questions. So I was thinking, I didn't quite follow the argument about the eddy packets when you're talking about in terms of the aspect ratios for wall-bounded flow being much larger than what you see in the jets. So why was that defining whether or not you see the eddy packets or not?
Oh, okay. So so first of all, the aspect ratio, these values are just, you know, some empirical values from the experiments. So the aspect ratio is related to the ratio between the streamwise length to the spanwise, in this case, streamwise to spanwise length of an eddy. So when aspect ratio is large, it means that we have a very long, you know, elongated structure, right? So when now the thing is that a single eddy is kind of is not too long, right? So when we have a single eddy or a couple of eddies, the aspect ratio becomes small. But when we have a large number of eddies, the aspect ratio can be large. So 28 is pretty long for, or pretty large for a single eddy. It shows that we have to have a large number of eddies to create such a long structure, if that makes sense.
Okay, yes, yeah, that does make sense. Thanks for answering my question.
Yeah.
All right, how about anyone in the audience?
Milad.
Oh yes, Min.
I mean,
you know, in wall-bounded flows, the small eddies are found at the wall, and as you go away from the wall, the eddies become bigger, right? In your case, are you implying that the small eddies are at the center line of your round jet, and as you go away, you get bigger eddies?
So the results that I presented, so it's important where you locate your reference sensor, right? So where you locate your reference sensor, it tells you where you are, or at which location you are looking at the eddy structures. In my experience, when I located the reference sensor at the center line, because around the center line, the eddies are kind of isometric. So I didn't get a very good view. First of all, the eddy structures were not self-similar at the center line. And also, yeah, they were smaller compared to eddies away from the center line.
But shouldn't it be the other way around? In the center line, the eddy should be large, and away from the center line, the eddy should be smaller, because anyway, eddies are no longer created once you exit the pipe.
So when we say away, so when I say far away from the center line, I'm not very close to the edge of the turbulent non-turbulence region. I'm still pretty much inside the shear layer, if that makes sense.
Yeah, it's sort of. I have to think about it. Thanks,
Okay.
Neil.
Thank you.
Thanks. All right. Anyone else have a question for our speaker? Yes, someone has their hand up. Saurabh. Oh, go ahead and ask your question. Sorry if I'm saying your name wrong. Yes.
Yes, I'm Saurabh Diwan. Well, I'm from Bangalore, India, and new to this audience, I got this link from Professor Gary Brown. So the question is, for the DNS data you showed in the cross where there are these circulating regions.
Okay.
Look at Did you look at the corresponding vorticity field to see if they really correspond to regions of high vorticity?
So yes, I did. For the vorticity field, it's better to look at the three-dimensional flow field. So honestly, I couldn't find a one-to-one relation for the high vorticity regions and these circular in-plane rotations, if that makes sense. And I think that's because we have three-dimensional effects, you know. So, but when I look at these three-dimensional flows, then I can actually see these three-dimensional eddies. But if the question is just in the inflow azimuthal planes, I didn't get a one-to-one relation. No.
Okay, so this inference is mainly from the velocity field.
Yeah. And by by just eyes, not a quantitative vorticity magnitude.
These eddies are not necessarily regions of enhanced vorticity.
Probably not. Probably not.
Okay. Okay. Thank you.
Yeah.
Okay. Thank you. We have another person with their hand up. Dilip, if you would like to ask your question.
Hi, Milad. It's Dilip here. Thanks for a great talk. It's really interesting. So just had like a couple of questions. So one is, all the self-similar eddies that you present here have the signature at the center line, right? So that's like the wall in wall-bounded flows. So
just so I want to clarify, probably I should have mentioned it during my talk, but I forgot. So in the radial arrangement, the reference hot wire was located. So probably I have written it here. So yeah, the reference hot wire is located at 0.6 times the jet half width. So the reference hot wire is not at the center line. But yeah, go on with your question.
Oh, okay. No, so my question was, are there any self-similar hierarchies that's probably not that do not have a signature at the center line? So I'm just thinking like detached packets of eddy in a wall-bounded flow, something similar to that.
I guess these are detached. Yeah, these are kind of detached. Yeah.
Okay. And the second one is, how well does the Taylor's frozen turbulence hypothesis hold in jet flow?
So I didn't test it. I could test it using the DNS data that I have, but I trusted this paper, Matsuda et al. So yeah, this paper, they have measured the convection velocity and showed that up to a radial distance of jet half width, the Taylor's hypothesis is very good. So yeah.
Okay. Yeah. Thanks, Milad.
Yeah, no worries.
Okay, so we have a question in the chat, although I'm not quite, I'll read it out, but I'm not totally sure what the question is asking. So maybe it'll make sense. At what Y on Y 0.5 location, so I think that was what you were showing earlier, is the Eddy model suggested? Rohit, if you can also unmute and ask your question too, if you want.
Yeah, I didn't get the question. So.
Yeah, maybe Rohit, if you could explain the question a little bit further, either in the chat or feel free to unmute and ask. It's not
I
quite
guess
clear.
the question was referring to this one. I'm not sure. But...
Yes, I'm not quite sure either. So maybe unless Rohit clarifies. Oh.
I might ask a question while the person is trying to find out where to put this question. You are interested in large structures, correct?
Well, both. I mean, yeah, eddy structures and very large scale motions. So if you mean the VLSMs, yeah.
And then how it's going to be if you are, instead of looking the whole data set, which is huge, probably in DNS, much more computational intense, looking at the POD modes, that means using a low order model to represent your flow field and use that low order model to predict these creatures, I guess.
Yeah. So the thing is that so this is something that has been kind of done. You can imagine that people love POD. so this is a study that uses POD to extract these very large scale motions, and in fact shows these helical structures. But what I'm interested in is the interaction between the eddy structures and VLSMs. So I'm not an expert in POD, so we can actually discuss this. If so, in the final slide that I showed. So here, using conditional averaging, I could extract this helical very large scale motion, and because because I'm not removing any scales, I still retain the eddy structures. So I computed these conditionally averaged VLSMs, and then computed the eddy structure field on that. And interestingly, I found these 3 eddy structures that are shown here. Now my question is that, can I do this with POD?
I guess it should be.
So we can actually discuss this.
The POD doing is finding your most energetic structures, which generally should be the large one, I guess.
Yeah.
That means you somehow filtering your data. But yeah, what's this last question, I guess?
Oh yeah, hi Milad. Oh, sorry.
Hi.
Can you hear me?
Yeah.
Yeah, great. Nice talk. My question was about the center line again. I know you've defined it as the geometric center line, but I was wondering, does the jet itself have large scale vacillations? And if so, would that mean that the center line is the appropriate reference point moving in time as well?
So you mean that center line could be in the instantaneously it could be moving around?
Well, it depends on the large scale oscillations of the jet.
So the location that we conducted the measurements at, it was quite far away from the jet exit. In my experience, I doubt that we had a lot of oscillations and non-turbulent region around there for the center line to be oscillating. And the other thing is that the Reynolds number is quite high, 50,000. Okay. So the jet is quite turbulent. So I doubt that the center line could be oscillating, to be honest.
Sure.
But,
okay. Yeah, I was just curious.
So these data sets are taken by Hotwire. So I don't have any visual,
Just one comment.
Oh, gotcha. Of course. Yeah. Right. Thank you.
Just one comment. Shouldn't we expect to have these oscillations if there is any in hot jet, not cold jet?
So in cold, this is a cold jet. So in cold jet, you don't think we would get any oscillations?
I guess cold jet is convectively unstable, but hot jet might be globally or temporally unstable.
Okay.
Then I'm not sure, maybe Vasilis can comment on that one too.
Sorry, got nothing for you. I was just thinking that because you're looking at large scale structures, just the presence or lack thereof of a large scale structure could shift the center line. But
Yeah,
I don't know.
no, that makes sense. But I've never thought about it in that sense. So I'll actually think about it to see how this affects the structures. Thanks.
Okay, cool.
Hi Milad, I'm Rohit.
Hi, Rohit.
So you have suggested the swirl structures of eddies. So my question was, at what y by y 0.5 location you have suggested those structures? So in later part you said that specific series of eddies will make a swirling structure. Yes.
Sorry. This one?
Yes. So the next slide to that.
Okay.
Yeah. So at what y by y 0.5 location, say they might be swirling with respect to the jet center, or I'm wrong?
Yeah.
Okay. So what is the rough location to it? Is it in the turbulent, non-turbulent region, or is it in the core of?
So these eddies are distributed everywhere in the jet. Probably, I'm not sure about the core. So, because with this data set that I have so far, these were from Hotwire. So I don't have a visual view. But with the DNS, I can look into this question more. So this is a question that I have myself too. If these eddy structures are actually common around the center line of the jet,
yes,
or more common around the shear layer. My first answer is that these are more common around the shear layer and less common around the jet center line.
Okay. Okay. Thanks.
But still within the turbulent region, not outside the turbulent flow.
Okay. So you're mentioning the shear layer where the Gaussian, the time average Gaussian profile have the maximum slope.
Yes, exactly. Yeah.
Okay. Thank you.
Okay, so we've had quite a few questions and discussion. Do we have any last minute questions before we finish up for today?
I might have a couple of more questions, but yeah. Milad, did you try to do the same analysis in the development region of the jet? Not fully turbulent region, in region around X over D 5 to 8 or 6?
Yeah, I did, and so I didn't present the data here, but if you're interested, you can look at this paper, which was published last year, International Journal of Heat and Fluid Flow.
Yeah.
So yeah, you have the name and everything. So the linear currency spectrogram doesn't look like this. We don't have this nice isocontours that are parallel to a constant line. And because you can probably imagine, because we have these dominant Kelvin-Helmholtz eddies, right? Circular eddies that dominate the other structures. So that eddy dominates these coherence spectrogram as well.
Another quick question. It's about your DNS data. Was it the compressible solver or is it incompressible solver?
Yeah. I'm not a DNS person, but you can to answer your question, you can look at the paper. So I don't have actually the title of the paper, so but I can email it to you. So I will look at the paper myself and answer your question. I'll email it to you.
Thanks. That's fine. Thank you.
Yeah, thank you.
Okay, I think we might finish it up there. We've kind of gone a little bit past the hour, so probably good time to finish things up. I'd just like to thank our speaker one more time for an excellent talk, a great start to the AFMS series for this year. And hopefully I'll see everyone next week. Okay, thank you.
Thank you, guys.
Thanks, everyone.
Thank you.
Thank you.